right, turn your textbooks, if you would, to page 229. I want to talk about a concept just for the thought behind it more than anything. Not so much for notes or tests or quizzes or anything. And it's this idea of projection. This idea of projection. Now, if we could get a visual idea or a mental picture of projection, imagine for a moment the sun really, really high, directly above you in the sky, so it's high noon. Projection would be the shadow cast by an object from an infinitely high sun. Now, the reason I mentioned infinitely high is this. Suppose for a moment that we had a tree, and the sun was not infinitely high in the sky, it was low over the tree. Well, then as the sun came down, its rays would cast a shadow that would come all the way out here, right? But if the sun is infinitely high in the sky, then the shadow would literally just come straight down from the edges of the tree. Does that make sense? That's the idea of projection, is that the light source, if you will, is infinitely high above the object, so the shadow cast would stay within the confines of its own shape. So, for instance, if I had a point, what would be the projection or the shadow of a point? Class?
Straight down.
Well, the projection wouldn't be a line, but we would draw a perpendicular straight down to get a point. The shadow would be another point. Does that make sense? If you had a line, what would be the projection of the line?
Another line.
Another line exactly the same length. Of course, all these other points would have their own projection, so that the shadow would be a line segment exactly equal to the other, right? Always, sometimes, never would the shadow be equal to the line. Would the projection equal the line? Sometimes. Only if the line is
infinitely high.
Well, the whole concept of projection involves infinitely high sun, but the line would only be equal
if it's a straight line.
If the line is
like flat.
Horizontal. There we go. Flat, parallel. Yeah, I get what you're saying, right? So you're saying that if the line, for instance, were at an angle, now the projection would actually be
straight down, like straight line down.
Compare the projection to the line. Smaller, right? If the line were angled in some way, the projection would be smaller. In fact, the projection of a line could be as small as
180.
a point. If the line were perpendicular. Again, if the line is like this, then its projection is a point. And then as the line begins to deviate from perpendicular, the shadow begins to get larger until eventually the line is perfectly horizontal. Then you get an equal line projection. Does that make sense? Look in your textbooks, if you would, page 229. Number 1 says, is the projection of a point always a point?
Yes.
Yeah. A point can't cast a shadow bigger than itself. Is the projection of a line always a line?
No.
No, we just showed an example where the projection of a line could be a point if the line were perpendicular or vertical, right? Can the projection of a line upon another line ever be greater than the line?
No.
No. Again, the idea of projection is that the light source, if you will, is infinitely high. So no, you're never going to get a projection that's actually bigger than the line you start with. Could it ever be less than the line? Yeah, if the line is tilted in any way, it will be. Would it ever be equal to the line?
Yes.
Only if the line is
horizontal.
Horizontal, there you go, good call. Good call. What's the projection of the hypotenuse upon one leg of a right triangle? Let's picture this for a moment. Okay, so we have our right triangle. What's the projection of the hypotenuse upon this leg?
The leg down is smaller.
Equal to the leg?
It's equal to the leg. The projection, again, if you imagine the shadow here, the shadow of this would equal the leg, wouldn't it? And of course, if you turned it the other way, then the projection would now be this leg, right? If we rotated it, well, now what's the projection of the hypotenuse? That leg now, right? This would be the shadow of the hypotenuse. What would be the projection of one leg upon the other leg? What would be the projection of this leg?
The hypotenuse. No, the bottom line.
The vertex of the right angle. That point, right? That would be the projection of this leg. And you can't get a projection of this leg unless you rotate it, and it would be a point, right? What if we rotated the right triangle to have the right angle up here? Now what's the projection of one leg?
Base. No, it's still at the
Half the base.
Not necessarily half the base.
Is it a rhombus?
The projection would be a segment marked off by the altitude, wouldn't it? What would be the projection of the other leg?
Other segment.
The other segment. So what would be the projection of both legs?
The whole base.
The entire hypotenuse, right? So just some projection concepts that you may talk about in higher math. I wanted to go ahead and look at with you there, and some thought that goes into that as well.
I like those.
However, back to stuff that you will be tested based on terms definition section of your notebook. Let's talk about what you read about in your homework reading, and then go a little bit deeper as well. Let's talk about area. Now, this is what junior high kids think of when they think of geometry. They think, oh, it's all those area formulas. How many remember those days? Well, it's all coming back. So if you learned your area formulas in junior high, this section should be initially easier for you. And then what we're going to do is we're going to up the ante a little bit and make it 11th grade level. Or it's still going to be 11th grade level. Good luck, 10th graders. All right, you got this. We're going to tie in some higher thinking into it. But on the surface, it's going to be very similar to what we did in junior high. Area, if you'll get this down in the terms definition section of your notebook, A-R-E-A, area, is defined as the number of square units contained within a geometric plane figure. The number of square units contained within a geometric plane figure. Area is defined as the number of square units contained within a geometric plane figure. So the idea being you've got some random shape and you have some square unit. I don't know how big the unit is. Maybe the unit is that big. Maybe this is a square unit. Well, you might say, well, but Mr. Dasky, you can't get a perfect square unit right here, though. No, but you can get a portion of a square unit, right? And there would be another square unit, and there would be another square unit, and there would be another portion of a square unit, right? Now, it almost looks like if you added these two pieces, it might make a full square unit, but I don't know for sure. And there'd be another square unit, and another square unit, and another. Well, you get the idea. If you added them all together, including the little fractional pieces of a square unit, that would give you the amount of stuff contained within, the number of square units, or the area of the figure. Does that make sense? Write this term down then, if you would. Equal figures. Equal figures. Equal figures are plane figures having the same area. Plane figures having the same area.
Doesn't that make them similar?
Plane figures having the same area. Let's just say, hypothetically speaking, that this particular figure here has, so let's just say 81 square units contained within it. Let's suppose that this also has 81 square units contained within it. That would make these two figures equal figures. Now, are they similar? No. Are they congruent?
No.
They're not even the same shape. But if they have the same number of square units within them, they would be equal. Does that make sense? So that any figure could be equal to any other plane figure, even though they may not be able to be similar, they may not be able to be congruent, they could perhaps be equal, meaning they have the same size. Similar means same shape. These definitely don't have the same shape. but they do at least have the same size, the same amount of stuff contained within. Does that make sense? Questions on equal figures. So a trapezoid and a triangle could be equal, class? A rhombus and a duodecagon? Yeah, they could be equal. Now, do they have to be equal? Certainly not, but they could be. Could they ever be congruent? No. Or similar? No. But they could be equal to each other.
It can't be similar to a square though, because a circle can't have.
In theory, a circle could be equal to another polygon.
How?
Well, again, pi may be irrational, but if you also had an irrational radius to the circle, then the area, again, in terms of pi, then theoretically a circle could have the same area. So yes, a circle could even be, because it's still a plane figure, so the area of a circle could theoretically, now, how to make it happen, that's going to be a challenge, but you could theoretically make a circle's area equal to that of, say, a trapezoid,
like
and they could be equal.
math?
I'm sorry?
Is that college level math?
It would require some, again, it would have to be computer generated to get it exact, and again, you'd have to have a ratio of pi in the radius to make the numbers work, which, like I say, would be perhaps challenging to actually draw and measure, but again, computer generated, you could make anything happen. So, all right, questions on that concept of area, this concept of equal figures. All right, well then let's get into some of our theorems for this chapter then. Theorem 68 is our next theorem. So theorems, corollaries section of your notebook. Theorems, corollaries section of your notebook. And we kind of get the idea with this goofy looking pentagon here that trying to subdivide it into square units is a bit of a challenge because the sides are so angular, if you will. But you understand a square like this would be very simple to break into square units. I mean, you just start, just make sure you mark off the same number all the way down, all the way across, and you're in business. Now, if the units didn't work out perfectly, you could just make the unit a different size, couldn't you? For instance, maybe square inches wouldn't work, but maybe 2 centimeters instead of an inch, which is slightly smaller, might fit. And you could do the same thing going across this way with a square. And the same would be true of a rectangle, correct? Now, again, you could make the unit whatever you wanted, but regardless of what it is, maybe you'd have to make them 4.5 millimeters a unit, right? Maybe 8.97, whatever. You could get crazy, but you could break any line down so that you would mark the same number of tick marks here as you would, of course, here, and then you would have a commensurate unit going up this way. You could break any rectangle down into a certain number of units this way, running all the way up, and then the same size unit, different number of them, running down this way. And of course, then we could count all the little boxes, right? And that would give us the area of the rectangle. But we know this, that if you were to count the number of boxes this way, and multiply by the number of boxes that way, that's a quicker way than counting each individual one. Let's take, for instance, some larger boxes that make our counting much, much easier. And of course, we'll say for sake of illustration, these are all equal to each other, since if I had the wherewithal and the time, I could make them all exactly equal, right? I could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20, right? But it'd be quicker to say that's 5 by 4, that's 20, right? So then we get this thought then for Theorem 68 that the area of a rectangle is equal to the product of its base and altitude. The area of a rectangle is equal to the product of its base and altitude. The area of a rectangle is equal to the product of its base and altitude. And if you would, after you've written it, write down this formula, R equals BH. R equals BH. We'll use the capital letter R to represent the area of a rectangle. We'll use the lowercase b and the lowercase h for the length of the base and the length of the altitude. On a similar note, then, Corollary 68-1. Corollary 68-1. Supposing we wanted to compare a couple rectangles' areas to each other. Well, since R equals BH, then it makes sense that you could compare one R to another R by comparing one BH to the other BH product. Does that make sense? Because they're equal. You're taking equals, dividing by equals. The answers would be equal. So corollary 68-1 says this: two rectangles are to each other. Two rectangles are to each other. Make sure you're not copying ahead, because that means you're not thinking about what I'm saying. You're just copying, which means you're not really learning. Two rectangles are to each other as the products of their bases and altitudes. Two rectangles are to each other as the products of their bases and altitudes. Two rectangles are to each other as the products of their bases and altitudes. Once you have that down, write down this formula if you would. R is to R prime as BH is to B prime H prime. R is to R prime as BH is to B prime H prime. Oh no, proportions again. Now you know.
It's been 1 2 days.
Two rectangles are to each other as the products of their bases and altitudes. So, given a rectangle with a known base and altitude, given some other rectangle with a different known base and altitude, the ratio of the areas would be the same as the ratio of the products of bases and altitudes. Make sense? Because the products of base and altitude are the areas. So of course that's the ratio of the areas. Make sense? Corollary 68-2. Corollary 68-2. Two rectangles having equal altitudes, two rectangles having equal altitudes are to each other as their bases. Two rectangles having equal altitudes are to each other as their bases. Two rectangles having equal altitudes are to each other as their bases. Well, we understand that R is to R prime as BH is to B prime H prime. But if H and H prime are the same value, then coming over here, they would cancel away, wouldn't they? In which case, R is to R prime as B is to B prime because the H is canceled, right? So the areas of two rectangles are to each other as their bases, if they have equal altitudes. On a similar note, corollary 68-3, rectangles having equal bases, are to each other as their altitudes. Meaning the areas of the rectangles. So when we say rectangles, we're referring to the size of them, their areas. Rectangles having equal bases are to each other as their altitudes. Rectangles having equal bases are to each other as their altitudes. If, for instance, this first and this third rectangle, if they have the same size base, then the comparison of their areas would be the same as the comparison of their altitudes. Why? Well, because, again, R is to R prime as BH is to B prime H prime, but if the B and the B prime are the same thing, then the B and the B prime would just cancel away, leaving us with R is to R prime as H is to H prime. Make sense? Same basic idea. Corollary 68-4. Corollary 68-4. The area of a square is equal to the square of one side. The area of a square is equal to the square of one side. The area of a square is equal to the square of one side. In this case, we know for a square that the base and altitude are equal to each other. So rather than call them by separate names, if I call one side S for side, the other must also be S for side. And if the area of a rectangle is base times altitude, then the area of a square would be base times altitude, or side times side, or side squared. If you would write this at the end of corollary 68-4, SQ equals S squared. Again, the SQ has a capital S, capital letters indicating area, lowercase letters indicating dimensions or sides in this case. SQ equals S squared. Other than making this comparison formula, these should be formulas we recognize from our junior high days. Now, we said A equals for everything in junior high. Okay, we differentiate letters to denotate different figures here. So R for rectangle and SQ for square, but otherwise should be very similar. Turn your textbooks now to page 237. And let's look at some math involving these different formulas. Let's take a look at some math involving these different formulas. Go ahead and read exercise number 1 there at the bottom of page 237 for us, Ethan.
Find the area of a rectangle. The base and altitude are as follows: 5 feet and 2.5 feet.
All right, so Ethan, if we want to know the area of a rectangle, we need to know the formula for the area of the rectangle. What is that formula?
R equals
BH. All right, what is it, Ethan?
R equals BH.
R equals BH. And since we're finding the area of the rectangle, we're going to keep the capital R for the area. In for the B, we should plug in the base they give us.
5 feet.
And in for the H, we should plug in the altitude or the height that they give us.
2.5 feet.
And to solve for the area, of course, it's as simple as multiplying. Now, it does help to have a calculator, it's true. But what do we get when we multiply 5 times 2.5, class?
12.5.
12.5. And notice our units are feet times feet, which would be feet squared. You could also say square feet. And it's important that area always be measured in squared units or square units. Metric, by the way, always uses the exponents. The English system can say SQFT for square feet, but I just always default to the unit squared because then I don't have to think about it and I'm lazy. Yes, sir?
In mathematics, do we most of the time use metric, or almost all the time?
In science, we will always use metric, so just get in the habit of using the exponent. That's my recommendation. All right, let's take a look at part B. Same thing again. We're finding the area of the rectangle, given the base and the altitude. This time, in part B, Genesis, the base is 8 inches, and the altitude is 1.5 feet. Thoughts on the base and altitude they gave us, Genesis? They're two different units. You can't have inch feet. You could have inches times inches, which is inches squared, or you could have feet times feet, which is feet squared, but you can't have inch feet. So one of these two units has got to change. We either need to make 8 inches become feet or 1.5 feet become inches. How many inches are in a foot, Genesis? 12. So I either need to multiply this by 12 to get how many inches, or divide by 12 to get how many feet. Which would you like to do, Genesis?
Multiply by 12 inches.
To get?
18.
Yeah, let's change the 1.5 feet into 18 inches. As a general rule, I like to default to going to the smaller unit because then I always get to multiply. You know, remember larger to smaller, multiply, coming back to you now. Your good old days when life was so much simpler, right? And so what would be the area of this rectangle, Genesis?
144.
Well, not inches, but inches times inches, which would be inches squared. Now again, would it be wrong to divide the 8 by 12 to get 2/3 feet times 1.5 feet? No. Go ahead and do that on your calculator. And you do get exactly 1 foot squared. Remember, maybe from your junior high days, that a square foot always contains 144 square inches. 12 inches this way, 12 inches that way. So 144 square inches contained within a square foot. Either answer would be correct, but I tend to lean toward multiplying by 12 to get the 18 inches and going from there.
Take off, like on a quiz or test?
No, either one's fine.
Just personal preference.
Just personal preference, because I'm lazy. Yep, good. Any other questions? Let's take a look at number 2, and read this one for us, if you would, Kendall.
The area of the rectangle is 75.8 square yards. The altitude is 5.2 yards. What is the base?
Now, again, here they're not asking for the area, Kendall, but we should still start with the area formula, which is?
Equals BH.
But this time they tell us the area, so Kendall, we know what to plug in place of the R.
35.8 square yards.
They also give us the altitude of the rectangle,
5.2 yards.
and we're looking for the base. Now notice they gave us decimals. If they're going to give us decimals, we're going to use decimals. You know I'm primarily a radicals fractions guy. But if they give you decimals, just use the decimals. What would I have to do to solve for the base here, Kendall?
Divide away the 5.2 yards.
Right, divide away from both sides. And what does that give us for the base of the rectangle, Kendall?
6.9 yards.
Good, 6.9 yards. Notice area is given with square yards. A unit like this, a dimension like this, will be plain old yards because we had 2 yards up here, 1 down here. This 1 canceled away one of the 2 to leave us with just 1, just like we would expect from algebra. Questions on this problem? Again, we can use the formula to solve for the base or the altitude if we know the area. Look at number 3. This one's interesting, Chris.
The base and altitude of a rectangle are in ratio 3 to 2, and the area is 254 square inches. Find the dimensions of the rectangle.
This is where geometry becomes 11th grade and not 8th grade. The base and altitude aren't given to us, but it tells us they are in ratio 3 to 2. Chris, how would I represent the base and altitude if they are in ratio 3 to 2?
3x and 2x.
Good. We know the area of the rectangle is
294 square inches.
294 inches squared. But we don't know the base or the altitude. What we did the last 2 problems, we did that in junior high. That's baby work. This is not something we did in junior high, where we have to represent the base and altitude in terms of x. But at the same time, it's stuff we've been doing all year. We should be good with this, correct? What would we do to solve, Chris?
Times the 3x and the 2x to get 6x squared.
Good, not 6x, 6x squared, so that, Chris, it takes me 2 steps now to solve for the x.
You want to get it set to equal to 0?
It's not a complete quadratic, so I don't need to set it to 0.
Why don't you divide 294 by 6?
Right, let's divide away the 6 to get
49.
49 inches squared is x squared. And then, like in the Pythagorean theorem,
C squared equals...
well, but like finishing the Pythagorean theorem, to get plain old x, I just need to
Take the square.
take the square root. There we go. And that'll give me x is equal to
7 inches.
7 inches. Good. The square root of 49 is 7. The square root of inches squared is inches. Now, but we're not done, right? X is 7 inches, but it never said find x. It said find the dimensions of the rectangle. And the rectangle's dimensions were 3x and 2x. So, Chris, let's finish it. What are the base and altitude?
21 inches or 14 inches.
Good. This is a 21 inch by 14 inch rectangle. Questions on now what is a little bit more geometry level. Okay? Do we see I was just stepping it up a notch? Not really doing anything different at its core, but just maybe having to do a little bit more algebra. Look at number 4. Read that for us now, Jamie.
Find the ratio of 2 rectangles, 8 feet by 12 feet and 6 feet by 9 feet.
Now notice it says there are 2 rectangles, Jamie. So let's find the ratio of 2 rectangles. What formula would we have to use here if we've got 2 rectangles and we're trying to find the ratio?
Will we use a proportion? Would be like 8 is to 12.
Quentin, from your notes, what I just had you write down. Audrey? There we go. Anytime you're comparing 2 rectangles, we're going to use the proportion. R is to R prime as BH is to B prime H prime. Say that with me, class. R is to R prime as BH is to B prime H prime. So, notice it's always been a rectangle. This rectangle of a rectangle of a rectangle. Now it says 2 rectangles. So, Jamie, that's my clue that I need to use the proportion.
R is to R prime as BH is to B prime H prime.
There we go. And I'm just trying to find this ratio of R to R prime. So I'm not trying to find R or R prime necessarily. I'm just trying to find the ratio. But they give me the bases and altitudes. So in for B and H, I may plug in
8 and 12
8
feet.
And 12 feet, okay? And then for B prime and H prime, I may plug in
6 feet and 9 feet.
Now, very conveniently, what's going to happen to all of the feet here, Jamie?
They'll cancel.
They're all going to cancel. And in fact, I could even reduce a little bit here with the 6 and the 8 and the 12 and the 9.
Would you cross out, would you have a 4 to the 3?
Okay, so let's make this a 4 and 3 like that.
Mm-hmm.
Okay. Anything else we could do?
Maybe the 12 a 4 and the 9 a 3.
Maybe make that 4 to 3. So if we were to then multiply, we would get
16 is to 9.
16 to 9. So apparently this ratio of the areas is a ratio of 16 to 9. Does that make sense? Finding the ratio of r to r prime, you just simplify down, reduce down. Now, to be fair, on your calculator, you could have said, well, I know 8 times 12 is 96, and I know 6 times 9 is 54. And you could have plugged in the fraction on your calculator, 96 54ths. And it would have reduced it, but it would have reduced it to 1 7/9. You'd have had to go back and make it improper 16 to 9 as a ratio. Maybe easier just to do it this way, and good practice with canceling questions on number 4. All right, turn the page. Read number 5 for us, if you would. Quentin.
Two rectangles are in a ratio of 2 to 3. H equals 6 inches, B equals 8 inches, B prime equals 12 inches, find A prime.
Once again, it tells us there are 2 rectangles. So Quentin,
R is to R prime, as BH is to B prime, A prime.
and it starts off by telling me what about these 2 rectangles?
Ratio of 2 to 3.
Now, that doesn't mean that their areas are 2 and 3. It means they're in ratio 2 to 3. So Quentin, I could represent the area of the 1 as
2.
they're in ratio 2 to 3. Call the one area 2x and the other 3x. However, if I represented them 2x and 3x, Quentin, what would happen to the x's anyway? They would cancel, because when it says that the rectangles are in ratio 2 to 3, then that means that this ratio is literally 2 to 3. Now, if you want to think through the x's, that's fine. It'll get you to the same point. But yeah, the areas of the 2 rectangles are in ratio 2 to 3. That is the ratio r to r prime. Do we all understand that? Even if you want to go with the, well, that means 2x and 3x. That's fine. The x's will cancel anyway, right? All right, so then we also are given some other values to plug in here, Quentin.
6 times 8.
I'm sorry?
6 and 8 for B and 8.
6 what and 8 what?
Inches.
6 inches for both? All right. And then down here in the denominator, the consequent.
B prime is 12 inches.
And we're finding h prime, is that correct? Do we see how to set it up? We got 2 rectangles. Use this proportion. Plug in what you're given. I'm given the areas are in ratio 2 to 3, so I know 2 to 3 is over here. I'm getting 6 inches, 8 inches, 12 inches, and finding h prime. I can cancel away these inches, right? Not this inch. That's important because that inch is going to come back when we get our final answer. Also, I can do a little more canceling.
2 and 12.
Careful.
6 and 12.
Right, you never cancel across an equal sign. You cross multiply across an equal sign, but you can cancel within the fraction to get 1 and 2. So if we were to kind of boil it down to where we're at now, I've got 2 is to 3 as 1 times 8 inch, or in other words, 8 inches, is to 2 times h prime, or 2h prime. Thoughts now? Yeah, we could cross multiply to get what, Quentin?
4h prime equals
24 inches. And that's going to give me?
h prime equals 6 inches.
6 inches. And there's the altitude. Easy enough?
Easy.
Questions on this? Now, you could, instead of canceling, if you're like, I'm really confused by all the canceling right now. That's okay. What you could have done was say 2 is to 3. You could have said 6 inches times 8 inches is 48 inches squared. And you could have left the 12 inches times h prime. And you could have just cross multiplied without canceling anything. That would have given you 24 inches times h prime is equal to 144 inches squared. and then just divide away the 24 inches from both sides, and sure enough, you're going to get 6 inches. So you don't technically have to cancel anything. I just like little numbers because I'm lazy. But you don't have to reduce or cancel. Questions on number 5?
That's how I did it.
All right. Let's take a look at number 6 now. Audrey, read this for us.
The dimensions of a rectangle are 9 inches and 12 inches. What are the dimensions of a rectangle 2/3 as large, cut off by a line A parallel to the base, B parallel to the altitude?
I know, Audrey, when it says it's 12 inches by 9 inches, technically they're not telling us which is the base and which is the altitude. So it's kind of leaving it up to us. Which do you want to be the base, which the altitude?
12 inches the base and 9 inches the altitude.
All right, so let's go and get ourselves a picture here. We've got a rectangle that is 12 inches by 9 inches. Okay, that's my rectangle. And we know the area, by the way, of our rectangle. If they give me the base and the altitude, they give me the dimensions, Audrey, I know the area.
How do you inches squared?
Now, Audrey, there's another rectangle we're going to make, and how big is this other rectangle going to be? 2/3 is large, right? How big would that be? Using your calculator if needed, how big would a rectangle be if it's 2/3 as large? Ooh,
72.
72. Take 2/3 of 108. Right, multiply by 2/3. Then you get 72 inches squared. So we're going to get another rectangle, class, that is 72 square inches, right? It's going to be 2/3 as big as this one. And we're going to get it, it says, Audrey, by drawing a line parallel to the base. Now I could draw a line right here, parallel to the base, right here, parallel to the base, here, here. There's a lot of different parallel to the bases I could draw. But question, what is the base going to be if I draw a line parallel to the base, Audrey? If I draw a line like this, parallel to the base, how big is the base of my new rectangle? 12 inches. I haven't changed the base because if you draw a line parallel to it, you're not cutting it at all. What I am cutting is the altitude, right? So this new rectangle that has an area of 72 square inches is still going to have a base of 12. What altitude must it have, Audrey, to have an area of 72 if the base is still 12? Remembering that R equals BH. We know the area is going to be 72 inches squared. I know the base is still 12 inches. What I don't know is the altitude I should have now. Right, I would need an altitude of 6 inches. So I would need to come up 6 inches, which is probably, relative to scale, probably closer to about here if we were trying to draw to scale. And now by drawing that line parallel to the base, I would have a rectangle that is 2/3 as large. Does that make sense? Now there's another way to think of this though, because if this rectangle is 2/3 as large, this area is to this area as 2 is to 3, 2/3 as large, right? And we know that these two rectangles, the first one and the second one, will have the same base. And two rectangles having equal bases are to each other as their altitudes. So if the rectangle's 2/3 as large, then the altitude should be 2/3 as large. Does that make sense? So figuring that out, that would have given us the 6 inches even quicker. Simply take 2/3 of the 9 inches. That's one way they wanted to form the new rectangle. The other way was, instead of drawing a line parallel to the base, Audrey, we could also draw a line parallel to the altitude. So now we need to come along here and draw a line that's going to cut off some rectangle that's going to be 2/3 as large, some rectangle that's going to be 72 inches squared in area, right? Question, what do I know about this new rectangle? Has the same 9-inch altitude. So if it has an altitude of 9 inches and it has an area of 72 inches, what is its base going to need to be? 8 inches, which by the way is 2/3 as large, right? Because two rectangles having equal altitudes are to each other as their bases. Does that make sense? Okay. Or you could say 72 equals 9 times b, divide away the 9 and get the 8, and that would work as well. Questions on this? Questions on this? You're going to have some practice with similar problems tonight in your homework. For now, look at Theorem 69 just below where we've been working. We're not done yet, just kind of throwing that thought out there that you're going to work with some more problems later. So you're there on page 238. And for sake of time, we're not going to copy the theorems right now. Let's just read them very quickly together. Go ahead and read Theorem 69 for us, if you would, Genesis.
The area of a parallelogram is equal to the product of its base and its altitude.
Does that sound really familiar?
Yeah, sounds like the one we just did.
Sounds like the rectangle, right? If you would, in your textbooks, inside that shaded orangey, yellowy, browny, whatever color that is box, write this formula, PL equals BH. Our formula for the area of a parallelogram. Now, how in the world does this work? Like, how could a parallelogram have the same formula as a rectangle? Well, we know that the opposite sides of a parallelogram are equal. We also, of course, know that they're parallel, and we know that all the angles are equal, respectively. If you were to draw any altitude anywhere in the parallelogram, the altitude would be perpendicular to both bases. If I were to literally remove this piece off, this parallel and these matching angles would have to line up perfectly over here, wouldn't they? And of course, this piece would still have this perpendicular cut off. And what I would now have is this portion of the base that was removed just simply shows up over here. So the base is still the same length it always was. The altitude is still the same height it always was. But instead of having a parallelogram now, class, it looks like a rectangle. So in a way, yes, a parallelogram is simply a rectangle. It's just that this isn't the altitude, that is. But the area is going to be the exact same. So yeah, it makes sense that the Theorem 69 would say that the area of a parallelogram equals base times altitude. Look at Corollary 69-1. Read that for us, Kendall.
Any two parallelograms are to each other as the products of their bases and their altitude.
Yeah, write this down in your book there. PL is to PL prime as BH is to B prime H prime. Yeah, we can compare two parallelograms then the same way we would two rectangles, because the formula is the same. Makes perfect sense. Look at Corollary 69-2 Part A. Read that for us if you would, Chris.
Two parallelograms having equal bases are to each other as their altitudes.
Because of course if the bases are equal, they'd cancel, and then PL is to PL prime is H is to H prime. Read Part B of that same corollary, Jamie.
Two parallelograms having equal altitudes are to each other as their bases.
Because if the H and H prime are equal, they would cancel, and you get PL is to PL prime is B is to B prime. Of course it makes sense. And then Corollary 69-3 is somewhat insulting, I suppose, but not entirely when you think about it. Read that one for us if you would, Ethan.
Two parallelograms.
Parallelograms. You can do it.
Parallelograms have equal bases and equal altitudes.
There we go. And on the surface, you're like, well, duh. Two parallelograms having equal bases and equal altitudes are equal. Of course that's true. Well, if you had rectangles, think about it. If you had two rectangles with equal bases and equal altitudes, they wouldn't just be equal, class. They would be congruent. But if you had two parallelograms with equal bases and equal altitudes, do they have to be congruent? No. Consider for a moment this parallelogram. Here's your base. Here's your altitude. Let's make an equal base. And let's take an equal altitude. Do not pack up. You notice they have the same base and same altitude. Definitely not congruent. In other words, don't lock in on the angle that is formed by the sides. It's all about what is the base and what is the altitude. They may not be congruent, but they'll still be equal. Turn over to page 240. Turn over to page 240. We'll do the math very much the same way. Look at question number 4. We already kind of talked about this, but may the area of a parallelogram be independent of the size of its angles?
What does that mean?
Think, use your brain. You're in 11th grade. Independent means it doesn't depend on it. Is it possible, may the area of a parallelogram not actually depend on the size of its angles?
Yeah.
Yeah, I just showed that. The angle doesn't matter. It's the base and altitude that matters, and we've already illustrated that. Look at number 5. The base of a parallelogram is 18 inches. The altitude is 6.4 inches. Find the area at your seats. And what do we get for the area, Quentin?
115.2 square inches.
And 115.2 square inches. You plug in the base, you plug in the altitude, you multiply them. Got your area. Same as you would have done for the rectangle, right? How many got the 115.2 square inches? Okay. Let's take a look at number 6. Here they give you the area of the parallelogram, 112.48 square feet. They give you the base, 15.2 feet, and they want you to find the altitude at your seats. And Chris, what you got?
7.4 square feet.
Ooh, careful. For the altitude, it wouldn't be in square feet. Just feet. There we go. 7.4 feet. It's just a length. So 7.4 feet. How many have the 7.4 feet? Again, plug in the PL, plug in the B, divide away the B to solve for the H. Pretty straightforward there. Look at number 7. Two sides of a parallelogram are 6 inches and 10 inches. And the included angle is 30 degrees. Find the area.
30 doesn't matter.
Notice they did not give you the base and altitude. They gave you two sides. They said you have a side of 10 inches and you have a side of 6 inches and the included angle of 30 degrees. But you don't know the altitude, do you? This is, well, that was what we've been doing, was junior high. This is 11th grade. By drawing this altitude class, I've just formed a triangle. Not just any triangle, 30, 60, 90 right triangle, where the side across from the 30 could be labeled X. That's my altitude. This side right here could be labeled 2x because that's the hypotenuse. And this piece that I don't care about could be x times the square root of 3. But if this hypotenuse is 6 inches, class, what is the altitude?
3 inches.
3 inches. Ah, now I know the base and I know the altitude. What's the area, class? 30 inches squared. This is 11th grade. Questions on what to expect. We're going to work on more of those in our lessons tomorrow. For homework this evening, you'll get a chance to practice with several of these. The homework is separately in the description of this video. It's not included for some reason, which I don't know, with the other handouts at the beginning of the semester. So get the handout from the description of the video if you're watching on YouTube. Obviously, those in class, just the handout that I handed to you. In addition to completing this handout for homework this evening, make sure you copy Theorem 69 and its corollaries. Make sure you copy Theorem 69 and its corollaries. We talked through them in class, but in order to finish by the bell, we had to kind of move quickly there. And there's one extra credit chance for you. Page 240, number 9. Page 240, number 9. It's going to involve a 30, 60, 90, which we'll do a lot of practice with in the days to come, but give you a chance at one tonight. All right, have a wonderful rest of your day, and you are dismissed.